Okay, in this video we're going to do chapters 2.2 limits and 2.3 continuity. So in our textbook it says the following about limits. So from a calculus perspective, when we study functions, we're looking at how changes in inputs affect changes in the corresponding outputs. Okay, so if we choose an input and getting closer and closer to a given number, will that corresponding output also get closer and closer to some number? So this is our focus on this section on limits. So here's a definition of a limit, and this is all going to be confusing until we deal with it for a little bit. So let g of x be a function and a is a number. We say that the number L is the limit of g of x as x approaches that number a, provided that g of x can be made arbitrarily close to L by taking x sufficiently close but not equal to a. So that is really confusing, and here's the notation that goes along with it. So this says the limit as x approaches a of g of x is L. Okay, so I have a function here. This is f of x. And it says, okay, the function to the right is f of x equals 2x minus 1. Let x approach 4. Okay, so right here is 4. So if we're approaching 4, we can approach it two ways. We can approach it from the left, and as we approach 4, what's happening? Well, let's say we're at 3, so we are approaching 7. See how we're getting closer and closer as we move up the curve? We're approaching 7 for that y value, or that L, as we get closer and closer to 4 from the left. Okay, so let's undo that just for a sec, and let's approach it from the right. So if we're going to approach 4 from the right, then that means we're going to approach it from this way. So what's going to happen is we're going to come down the curve, and we're still going to get closer and closer and closer to 7. Since we never actually get to 4 in a limit, we also never actually get to 7. But notice that when I approach 4 from the left and from the right, I approach 7 from below and then from above. So I'm converging on 7. So in this situation, 7 would be our limit. All right? So you have a slight idea now of what limits are going to be. So in the next slide, we're going to evaluate these limits algebraically using a table. So that comes next. All right, so we're going to use the exact same function. F of x is 2x minus 1. It's just a line, nothing intimidating. Okay, so we're going to approach 4 from the right. So notice, if we approach 4 from the right, we're approaching 4 from the higher numbers. So we indicate that by this plus sign right over here. You see that plus? That is telling me I'm approaching it from the right. If I approach from the left, you're going to have a 4 with a negative. It means that you're approaching from the left, so therefore the numbers that you're hitting are below 4 and getting closer and closer. All right, so here's our table. Approaching from the right, I'm at 4.1, and then I go to 4.01, 4.001, 4.0001. So you see I'm getting closer and closer. If you were to plug this in, it's hard for me to write a whole lot with this cursor, but you would get a 7. Let me try this again. Let's see if we can make a different color maybe. This will be a 7.2. And see if you can do the math and get that. This will be a 7.02. So you're kind of going down the curve. This is 7.002. and 7.0002. So you can see you're coming down and you're getting closer and closer to 7 when you approach from the right. Approaching from the left, I'm going to go higher and higher towards 7. So this is 6.8. This would be 6.98. This is 6.998. 6.9998. So from the left and from the right, we are converging on an L, or a limit, of 7. And again, just to clarify, I'm taking these numbers and plugging them right in the function. And then I'm getting these values for f of x. Same thing here. Take this number and plug it in here, and you'll get 7.2. Okay, so now let's take the exact same function, and we're going to approach 3 from the right, that's the plus side, and from the left. So once again, take this number and plug it right in there. And if I do that, I'm going to get 5.2. If I plug 3.01 in, I get 5.02. If I plug 3.001, that's going to give me 5.002, and so on. You can see I'm getting closer and closer to the number 5. So when I approach from the lower side, excuse me, from the left, what happens is I start out at 4.8, and then I jump to 4.98, 4.998, 4.9998. So when I approach the number 3 from the right side and from the left side, I am converging on a limit of 5. So if I asked you to do it with a table, that's how you would indicate it. But remember graphically what we were doing. So if I just pop back for a second, we were coming up the curve when we were approaching from the left, and coming down the curve when we were approaching from the right. So we're doing the same thing with the table. It's just another approach. So let's continue. Okay, now we're going to look at some graphical representations of functions. So this function right here is a piecewise function. So if I asked you to tell me what is the limit as x approaches 4, so I'm going to approach it from the left, the lower side, so I'm approaching 4 this way. When I do that, I'm coming up this part of the curve, and I am approaching the number 6. When I come from the other side, grab a different color, here we go, I am approaching from the positive side, the plus side, the higher side. I'm coming this way, and I'm going across this part of the function, and I'm approaching a value of 8. So, very important point. If you do not approach the same value from the left and from the right, you announce that the limit does not exist. All right? Let's look at the next one. What is the limit as x approaches 4? So I'm approaching from the, let's be consistent, from the left. I'm approaching 4 on the x-axis. When I do that, I climb up the function, and I'm approaching 4. When I approach from the right side, from the higher values, from the plus direction, I am coming down the curve, and I am still approaching 4. So in this situation, it's interesting to say that even though this is a hole right here in my function, as I approach from the left and from the right, I'm converging on the same y value, the same L, of 4. So therefore, I would say the limit of this function as x approaches 4 is going to be the y value 4. Even though at x equals 4, there is no function because it's a whole, it still has a limit. So let's go back for a second and look at the first function we talked about. What's the value of this function at 4? Well, look, right at 4, right here, I have an open circle, so there's no value there, but there is a value right there, and that value aligns with the 8. So if I were to evaluate this function at 4, I would get 8. If I were to evaluate this function at 4, I would have to say that the function does not exist there. So that's not applicable. All right, let's stick with limits. Here I want to figure out what happens, what's the limit as x approaches 2. So if I approach it from the left side, I'm coming here along the x-axis, and when I do that, I'm coming up the function, I'm getting lower and lower, and I'm heading to negative infinity. When I am going from the higher part of the x-axis, from the plus side, I am going up this curve, and I am approaching, getting closer and closer to positive infinity. So we would say the limit does not exist because the function is not heading towards, is not converging towards the same thing. It's not converging towards positive infinity. It's not converging towards negative infinity. It's converging opposite directions. Therefore, we would say the limit does not exist. And what's happening right here at 2? We have an asymptote, so the function does not have a value there. All right, so we've kind of gone through a lot of limits here. So let's think about what I'm saying here. Things to consider when looking at the graph to determine the limit of a function. We're going to check the limit from the right and from the left, and it's very important. If limits do not approach the same value from the left and the same value from the right, then we say the limit does not exist, and you can write that as DNE. The limit does not exist. So we're going to talk about some other additional functions we're going to analyze graphically in the next page. Okay, so look at this first example. We want to determine what is the limit as x approaches 1. So we're approaching from the left, from the lower numbers heading on up, and it looks to me like we're coming down the curve over here and approaching the number 3. Let's try to do it from the right. When I approach from the right, I'm coming from higher numbers approaching the number 1, and when I do that, I come up the curve. I'm coming up the curve, and I'm also converging on the number 3. So we would say that the limit as x approaches 1 of this function is 3. That also happens to be the function value at 3. So at 1. So f of 1 equals 3, and that's also the limit, and that's because you have a parabola that's not complicated. What about the next one? Here is a cubic function, so x to the power of 3. So we're aiming to figure out the limit as x approaches negative 1. So if we approach from the left, I am going to be coming down this curve, so down the curve, and it looks like when I get to negative 1, I'm approaching a y value of 2. So let's head from the other direction. From the positive direction, from the higher numbers, as I approach 1 this way, I'm coming up the curve, and again, I'm converging at 2. So I would say the limit of f, or I guess this is g of x, as x approaches -1, that limit will be, and what did I say it was? 2, right? 2. Okay, that also happens to be the function value. If I evaluate this function at -1, I get a value of 2. So it just so happens that my limit and my function value are one and the same. All right, let's go to the next one. Here's a rational function. If I approach -2 from the left, so on the x-axis it's here, on the curve itself I'm climbing up, and I'm approaching infinity. As you approach from the right, from the higher numbers coming down, I'm going this way on my x-axis, and I'm coming down the curve, and I'm heading towards negative infinity. Because we're not heading the same place, we would say the limit does not exist, and also there is no function value at x is -2 because there is a vertical asymptote. So more things to think about. Let's keep going. Okay, here I've put together the 6 limit theorems. So in our textbook, they present these. We are not going to really do this too formally, but I have some examples down below. But so we'll just kind of read through this now and see what we think. Okay, so the limit of a constant is a constant. So because there's no variable in here, the limit is just the constant itself. The limit of a constant and a function is the constant times the limit of the function. So this is a lot of theory, a lot of algebra. If r is a positive constant, then this is how we are going to express this. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. And the limit of a quotient is the quotient of a limit, provided that you are not forcing yourself to divide by 0, which you can never do. All right, so there's a lot of theory. Let's now apply that theory and see if it makes sense. Okay, this is the algebraic approach to limits. So it's kind of a formalized approach. So if you want the limit as x approaches 3 of x cubed, what you would do is take the limit of x and cube it. So the limit of x would be 3. 3 cubed is 27. That will be your limit. Okay, so then let's do the next one. It's a parabola. The limit of x, the limit as x approaches 2 of this function. So pull out your constant, take the limit of x, and then square it. Then the limit of 7 is just a constant, so it's just going to be 7. So you end up having 5 times 2 squared, so that's 5 times 4 is 20. So this is 20, plus another 7 gives us 27. Okay, let's deal with a radical now. So we're going to bring the limit inside next to the x, the limit of x. If x is 1, that's 1. 1 squared is still 1, plus 8 is 9, and then take the square root of that, which is 3. So that's how we're getting that. So what do you think about this next one? The limit of 4x squared. So what I would do is I would say that's going to be the limit of 4 times the limit of 5, and then we're going to square it. So that's going to be 100, right? Because it's going to be 4 times 5 squared. 4 times 25 is 100. So there are more practice problems on page 97. But in these cases, the function has a value at the x selected, and that value is the limit. This is not always the case. So this method we're going to call the plug it in method, okay? When you're trying to find a limit algebraically, you always try to just plug the number in. If you get an answer, you're done. If you don't get an answer, or if you are forcing yourself to divide by 0, then we have other options. And the other options are algebraic manipulations, and they're probably going to come pretty soon. So let's go to the next page. Okay, so look at our first problem here. If we try to take the limit just like we've been doing it on the previous page, the plug it in method, look what's going to happen. The second you take this 4 and you plug it in the denominator of the rational function, you will be divided by 0 and game over, nothing exists. So, the plug it in method doesn't give us a result. So then you have the option of using an algebraic manipulation. And in this situation, the algebraic manipulation we would use would be factoring and canceling. So this is what we're going to do. So we're still going to try to take the limit as x approaches 4. But since we know when we peaked, we end up having a divisor of 0, which you cannot have, we're not going to take the limit yet. First, we're going to factor the numerator because that's a quadratic. So we're going to factor and we're going to cancel. When we cancel, look what's happening. We are eliminating the denominator that went to 0. At this point, take the limit. So plug in your 4. 4 plus 4 is 8, and that is the limit. Now, what we have discovered is that if we were to plot this function, this is what it would look like. It would be a line, but it would be a special line. So if this is 4 right here, say, that's 4. Okay, so here's our line. At x is 4, something special is going on. At x is 4, we have a hole in our function. So the hole in the function means that there's not going to be a value. So let me just erase this for a second. There is not going to be a value at that place. Okay, I can't say that our function has a value of 8. What I can say, and let me move this a little bit so I can do some more talking. What I can say is that the limit as x approaches 4 is 8. So guess what number is right here? It's 8. So if I approach from the left or I approach from the right, I'm going to be approaching the value of 8. And by doing this algebraic manipulation, I get rid of the fact that I don't have a value of the function at 4, but I do have a limit, because from the left and from the right, I am converging on a y value of 8. And doing the algebraic manipulation of factoring and canceling reveals that. So there's one more manipulation we're going to talk about, and that's dealing with radicals. So we'll do that in the next page. Okay, so on this page, we have our radical, and it's right here. And so looking at this, if I'm trying to figure out the limit as x goes to 0, I'm seeing the second I plug a 0 in down here, I'm dividing by 0, and that's not good. So that is telling me that this particular function does not have a value at x is 0. Now the question is, does it still have a limit? And in order to reveal the limit, if there should happen to be one, I'm going to use a process that's called conjugate pairs. So I want to get rid of that radical. I want to get rid of the x in the denominator, really. So this is what I'm going to do. So I want to take the limit as x approaches 0, but I don't want to take it yet. So first, we write our function, and then we're going to multiply by the conjugate pair. So, by the conjugate. So what is the conjugate to this numerator? Well, it is, you write exactly like what you see, and then change that operation. Okay, so the first term is exactly the same, and then you change the operation. And then the last term is the same. So, what is this that we just built? This is just a fancy 1. It's same over same. You can always multiply by 1, and you never change anything. So I'm going to use that algebraic manipulation. I'm still trying to take the limit as x approaches 0. Okay, if you FOIL the numerator, what you should end up getting is x plus 4, because the radicals go away. Then the middle terms will cancel each other, and then you're going to get a positive 2 times a negative 2. So that's going to be a negative 4. And then you have an x down below here, but then you have this whole conjugate down below. Okay, so what do I have now? The 4's, I'll change colors here. Okay, the 4's can cancel because they're opposite signs. Now the x's can cancel, and that's a great thing, because that x that stood alone in the denominator was causing us a big problem because it wasn't letting us take the limit. So now look what I have. So I'm going to do it one more time. Limit, I'll just change color here. As x approaches 0, what do I have left? Well, I have a 1 in the numerator, and then in the denominator I still have an x plus 4, and then a plus 2. Okay, plug in your 0. Since I'm plugging it in, I'm not going to write the word limit again, because I'm plugging in the 0. So I have radical 4, because 0 plus 4 is just 4, plus 2. So that's going to be 1 over 4 when we're all said and done. So what does that tell me? It tells me that even though this function does not have a value when x equals 0, which means you can't just plug it in and get a number, it does approach a number as x gets closer and closer to 0 from the left and from the right. What is the number it's approaching on the y-axis? That number we've discovered is 1/4. So this has given you some background with limits, but let's continue. Okay, up to this point, we have been discussing limits as x approaches a number. Now we're going to talk about limits and infinity. So notice that x is approaching infinity. So we're going to be thinking horizontal asymptotes, and that's going to become apparent very quickly. So can you sketch the graph given the limits below each one? So this says the limit of my function is 4 as x approaches infinity. Okay, so the y is going to be approaching 4. So let's just see where 4 is. 4 is right there. So this is telling me as x gets bigger and bigger, my function will approach 4. So what could that look like? Well, it could look like this, couldn't it? If this was my function, isn't it approaching 4 as the x gets bigger and bigger? And hopefully you're saying yes. Okay, let's look at the next one. What's the limit as x approaches, that says negative infinity. So as x approaches negative infinity, they want my function to approach -1. So where is -1 on the y-axis? There it is. So as my x values get smaller and smaller, so smaller and smaller and smaller, the function will approach -1. That's how that looks. Okay, so that's a graphical representation of it. Let's talk about it algebraically, and we'll do that on the next page. All right, when you are looking at algebraic examples of the limit as x goes to infinity, you can kind of think this out. If you only have an x in the denominator, it's just one place. What is happening to this fraction as x gets bigger and bigger and bigger in the denominator. If you have 3 over a huge number, okay, plus 3 more, 3 over a really, really big number, isn't that fraction going to 0? Because you have 3 over 10, 3 over 100, 3 over 1,000, 3 over 1,000,000. Do you see how that fraction itself is getting closer and closer to being just worthless? So this limit, as x approaches 0, with this simple situation, so the limit as x approaches infinity, I should say, will equal 0. So what does that tell me? That's telling me that as my x's get bigger and bigger and bigger and bigger, my function will go to 0. Okay, now what if we have x's in the numerator and in the denominator? It's a little hard to understand what infinity over infinity actually means. So we have to do an algebraic manipulation. And the algebraic manipulation that's needed is to divide by the highest power of x that's present in the function. So the highest power of x is x to the first. So what I'm going to do, before I take the limit as x approaches infinity, I'm going to take every single term, and there are 4 terms, and I'm going to divide every last one of them by x. And because I'm doing the same exact thing to every term, I don't have any algebra problems in doing it. I'm not changing the value of the function, I'm just changing how it looks. So once you do that, reduce your functions, and I end up having 8 minus 5 over x over 2 plus 3 over x. Okay, so let's think about this. As 5 over x, as the x gets bigger and bigger and bigger, isn't that going to go to 0? 8's not changing, but 5 over x will approach 0. 2 won't change, but 3 over x will approach 0. So 8 minus 0 over 2 plus 0 is just 8 over 2, which is 4. So this limit, as x approaches infinity, will equal 4 for the second function. Okay, so we are looking at horizontal asymptotes. So that's what we're really doing here. So what do I say in the bottom? Note, it's helpful to view taking the limit as x approaches infinity as finding the horizontal asymptote. And actually, it's just finding the number associated with the horizontal asymptote. If I was really finding a horizontal asymptote, I would have to say the horizontal asymptote is y equals 4. But when I'm finding the limit, I just say the limit is 4. Okay, so let's continue on. Okay, in this section, we're going to talk about continuity. So we've covered 2 sections in this video. So here is the continuity piece of it. Okay, a function is continuous at x equals a, provided that its graph has no breaks or gaps as it passes through the point a comma f of a. So can you identify the reason why the following graphs are discontinuous? And where does this occur? So think about trying to draw this graph. Here I am, I start drawing, I'm all good, drawing is fine, but now I have to pick up my pencil right here to get above. And I pick it up again right here. Wherever I have to pick up my pencil, and I had to jump to another level, that is a jump discontinuity. Okay, there's a gap in the function is not continuous. Here's another example. Here's a gap in the function is not continuous. It has a jump discontinuity. Alright, so it's all about sketching your graph. If you have to pick up your pencil to finish sketching it, it is not continuous. And you can identify the x values where the function is not continuous in these two sketches I have. Okay, let's continue this discussion on the next slide. Okay, so in the previous slide, we talked about jump discontinuities. We're going to discuss two more right now. So, looking at the graph below, so this graph right here, we have an infinite discontinuity at x equals -1. So look what's happening. I'm drawing my graph, and then look, I'm going up, 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 and then I have to jump, and I'm coming up from the bottom now. So that is called an infinite discontinuity. Now, at 7, or at -7 rather, right here where this hole is, I have a discontinuity there as well, but that's called a removable discontinuity. And that one was tied into the limit. Remember we said we had no function value where you have a hole, but you could have a limit? Well, it's also tied into discontinuities. So I have a discontinuity here, but it's considered removable because it's a simple hole and I get a limit with it. So there is a connection between limits and discontinuities. So here's the connection. So the limit definition of continuity, a function f of x is continuous at x equals a provided the following limit relation holds. So the limit as x approaches a has to be the same as the function value at a. So when you have a hole, there is no function value at a. So the limit definition of continuity tells us about that. So I know, because even though I have a limit, because the limit doesn't equal my function value, I have something going on there, and in that situation where x is -7, I have a hole. So let's go on to the next slide. Okay, in this last slide, if you open your PDF up on the computer, you can have access to these videos. They're all from Khan Academy, and I think you're going to find them very helpful to understanding some of this material. So our textbook talks about unbounded limits, and Khan Academy will do that as well. So if you have a function that it does not have restrictions on it, it's considered unbounded. There's also a nice discussion of piecewise functions here. There's Khan Academy on limits by direct substitution, which is what we've been doing, and Khan Academy on limits of piecewise functions. So I would say look at 1, 2, 3, 4, these 4, and that in conjunction with listening to the rest of my video and reading our chapter, you should be able to do the homework assignment, and then we can discuss it in class.